Thank you. So we saw where moment of inertia comes from, and I think, went a little bit further and talked about where rotational kinetic energy came from, right? We derived them both at once. And at the end of that discussion, we were able to show that 1/2 times, and inside here was like m1 r1 squared plus ... equals omega squared. And so we were able to say that from kinetic energy, you can derive moment of inertia, or at least the semblance of moment of inertia, and that for the whole object, should the whole object be rotating at a common angular velocity, then this would be its rotational kinetic energy. And indicated that if its center of mass was moving, then the total kinetic energy would be the sum of these two things. Is that what we talked about? What we're going to talk about today is twofold. The first is I want to make the argument that you have quite a bit of knowledge from first semester related to net force. We started with Newton's laws, and I should probably add in here, F1 on 2 equals negative F2 on 1, right? The three of Newton's laws. We teach things as distinct units, but that's not how physics is really designed. As a study, these things are all interrelated. We indicated that the use of a single force can be to change an object's energy. In fact, we described that as a function. So if we could add up the force as it causes an object to move, that would be an indication of the change in energy of the object, or the energy transferred between one object and another. So the method by which you change something's energy is through force. And we had, as you probably remember, different ways of kind of writing it, depending on how complicated the force and displacement arrangement was. Now, you can have a situation in which the net force on the object is 0, but energy was still transferred to the object. I push a box across the floor, I'm giving the box energy, friction is acting on the box, it's taking that energy away. So that's a case where both forces were doing work, but the net effect was that the object's in a new location but isn't moving. Its energy hasn't really changed. It was just a conduit by which the energy left me, went to the box, and went to the floor. But of course, if the work is being done by an unbalanced force, here, there's an acceleration. That acceleration causes a change in the object's velocity. That's the situation in which net work was done. And we now have a change in the kinetic energy. And we also indicated that if we do work against a conservative force, that also causes a change in the potential energy. We developed all of this so that we could get a conservation of energy explanation. But it's all just energy. And although I've repeated that motive several times over the course of this conversation, what I mean by that is if we want a picture of the energy of an object, well, now that picture has expanded to include not just its translational motion, but its rotational motion. And I think that you guys are sophisticated enough to understand that there might be other forms of energy associated with the object that we also have not really gone into here. And there are other forms of energy still available because there are other interactions that we haven't exploited yet. So there's thermal energy, and there's chemical energy, and there's other ways in which energy can interact. But we've really kind of narrowed down the two forms of energy that are dealing with motion. Right? There might be other ways in which an object is moving. Now, at the same time, in a separate unit, we talked about when a net force can be used to change an object's momentum. We indicated that this was impulse, and that an impulse conversation or an impulse discussion was about something similar to but distinct from the way in which we talk about energy. An object can have energy and momentum at the same time, of course, but they're different parts of the picture. One of them is more aligned with talking about what's happening to an object, while one of them is more aligned with talking about the interaction between one object and another. But both of them paint a picture of what the object is doing and help us predict what the object will do in the future. We indicated through contact that the impulse experienced by one object has to be equal and opposite to the impulse experienced by another. This is the implication of Newton's third law and led to our whole concept of how we deal with conservation of momentum and collisions. Rotational motion isn't a separate study. Rotational motion is central to this understanding, right? It's a part of this. It's still the same study. We are just adding a layer of understanding, something else that we can do to try and predict the behavior of a system. Because most of our system isn't made up of blocks. It's made up of things that are of unusual shape that move in many different ways. A car doesn't just go in a straight line and suddenly it's going in another direction in a straight line. It had to transition, and while it was transition, it was rotating to meet the needs of its new direction. So there was rotational motion. We glanced over that, but there had to be a torque to cause a change in the orientation of the car. And of course, the whole car's engine, although it's being transported all over the place, if it's an internal gasoline engine, we're talking about something that is rotating all the time. The car itself just looks like a box, but there's a lot of this going on in there. So although it shouldn't be a stretch to consider work from two different angles, one of them being work done by a force, but is it too hard to recognize that there's got to be some kind of similar analogy to work done by a torque? And it's got to work this way. And I don't want to, spend a lot of time on this because I doubt this would ever show up on the exam, but this would be the same kind of calculation, although the cosine wouldn't make as much sense here. And because our torque is either going to cause clockwise motion or counterclockwise motion, it's not going to be somewhat in the direction of the motion. That's been taken care of by the cross product that we deal with when we get torque. On the other hand, be careful of the units. This is meter newtons times radians. Radians isn't necessarily a unit in a traditional sense, but it has the effect of making this a Newton meter or a joule, right? Because that's what it would do. Our answer would still be in joules. In fact, if this was being done by an unbalanced torque, then it would be a change in rotational kinetic energy. All the same things we had before. Again, energy is energy. It all works together. It's just another form. That's not true when we talk about momentum, the other side. Linear momentum is different and distinct from angular momentum. They don't add together. They're not the same measurement. They are different measurements. An object can have linear momentum, and an object can have angular momentum, and it can have both. But they are measured differently. They are complementary, but they are measured differently. So when we talk about angular momentum, we're going to have to be a little bit more particular. It's got different units, so they don't add together. There are collisions that involve angular momentum, but we also have unique situations with angular momentum that we don't have with linear momentum. With angular momentum, we have the situations where an object's moment of inertia can change while it's moving. We didn't worry about that with linear momentum. We did have the idea that an object's mass could change while it's moving. But with angular momentum, an ice skater can start spinning, have angular momentum, and then change the orientation of their arms. That changes their moment of inertia. And because it changes their moment of inertia, if they are easier to turn, that's going to affect their angular velocity. That's why they can change their speed without necessarily having to apply work or apply torque to their body. They can start a spin, remain spinning, and manipulate their speed by manipulating their moment of inertia. So angular momentum is different and will have different tenets to it. So when we get to that, which will be early next week, be prepared. We have some things to deal with. Energy, though, is relatively easy. And And we started this yesterday, so I kind of want to continue it today. 20 minutes spent, or 10 minutes spent on this and trying to remind you about all the stuff we talked about when it came to energy. So let's do a quick trip down memory lane. Perhaps. I kind of leaned into Anthony today in the middle of a sixth period in doing this question. I wasn't mean, but have you met Anthony? You guys know. I don't have to say even a last name, and you know who I'm talking about. That's how I know you know. So they changed less successful than I want you guys to be right now. In this problem, let's say that we have a situation in which the coefficient of friction is 0. And let's say the object it's just a box, mass m. You should have absolutely no difficulty telling me how fast the box is going at the bottom. Like this should be like maybe memorized, but you should certainly be able to work it out. And what I found was that not just Anthony, but several people, they had difficulty. They were talking about forces and stuff, and I was surprised and shocked because I don't give you the angle of the ramp, right? With what's there, you should be able to almost instantly tell me how fast it's going at the bottom, especially when you've had an entire lead-up that spent so much time talking about energy. So who should I pick on to tell me the answer? Harishi? You're in my line of view. Well, how fast is it going when it reaches the bottom? Do you need a second? I'll give you a second. I'll give you 30 seconds. Maybe you can confer with your scholarly neighbor. Yeah, square. We have two different methods that you could have used to figure this out. Two. One of them is you could have made a reasonable force argument. You would have had to use a placeholder for the angle and a placeholder for the length, but you would have gotten that the acceleration down the ramp is mg sine theta, and that the length is L. And if you did the work, you would find out you could get it converted to H. But the best way is just say it's mgh here at the top. That's how much gravitational potential energy we have. And down here, it's 1/2 mv squared. The fact that you guys couldn't jump on that fast and realize it's got to be a square root of 2gh tells me that even with that was just not enough to jumpstart you into this question. But now are we jumpstarted into this question? Even though I introduced it yesterday? Good. Let's talk about making a change, because we need to make this about today. How does this change the problem? Be careful. As long as this is still true, it doesn't change the problem. Right? Slides down to the bottom. For there to be rolling, there has to be friction. So our problem is different. We can't directly compare the block sliding down the ramp with a block rolling down the ramp, because a block sliding down the ramp is going to experience friction, and that's going to slow it down. But a block rolling down a ramp, again, is going to experience friction, and that's going to slow it down. The difference is the block rolling down the ramp is experiencing a frictional torque that, instead of taking energy out of the system, is converting the object's potential energy into rotational kinetic energy that will slow it down. The block that slid down the ramp, all of its energy was dumped into translational kinetic energy when it's at the bottom. But an object that rolls down the ramp makes it to the bottom of the ramp spinning. And because it's spinning, Some of the energy is translational, but some of the energy is now rotational. Does this object have any more energy than the block had? Still mgh, right? The difference is now the amount of energy the bottom block has at the bottom, or the whatever the rolly thing is at the bottom. That energy is now split up. Some of it is rotational kinetic energy, and some of it is translational kinetic energy. It will be slower at the bottom because it had to divide up the energy. The difference is, unlike a box that might slide down the ramp and experience friction, the amount of energy taken away by friction is gone. When an object rolls down a ramp, the energy is not gone. Friction didn't take away energy. It transferred energy. So it has the same amount of energy at the bottom with no loss. Now, you guys are smart people. I should just say to you, pick a shape and work the problem. Tell me how fast it's going at the bottom. In fact, I think that's how I'm going to do this class. So there's 10 minutes left. Pick a shape, something that rolls. Disk. All right, this object is a disk with a moment of inertia of 1/2 mr squared. I'd like you to tell me an expression for the velocity at the bottom. This is a small class, and I'm not running behind, so I think you can do this. I'll tell you something. It's rolling. The moment I said that it's rolling, that there was sufficient friction for it to be rolling, I gave you something that you might be able to use so that you can solve this for V. I want V. And it's not going to be a surprise. V is going to be the square root of something times GH. So you'll know you got it right if you get the something right. I'll give you 60 seconds.
Got the square root of 4 over 3 GH.
Square root of 4 over 3 GH. A little disappointed because that's the right answer. So would anybody like to see how that's done?
Yes.
All right. But tell you what, I'm not going to do it the way Harishi did it. I'm going to stick with I until the very end. And then when we get to the end, I'll put the value in for the disk. It is easier to put the moment of inertia in for the disk first. It is easier. It makes it an easier problem to do. But I'm going to purposely, since I think that's how probably most of you who are successful did it, I'm going to put the moment in last, and then we can put any moment we want in. Does that make sense? All right, so the first thing I'm going to do, because I'm not plugging in for I, is I am going to try and get them both in terms of the linear velocity. You don't have to. You could put it in terms of the angular velocity. Then you'll have R in your problem because the angular velocity is going to be based on R. So I'll put everything in terms of the linear velocity. All right, so I have a 1/2 on both terms there, so I'm just going to multiply through by 2. And I'm going to collect the V squareds. That's going to give me just M here, but on this side it's going to give me I divided by R squared here. All good? All right, so now I want to solve this for V. And I'll have 2mgh all divided by m plus I over R squared. Now, I'm not nervous about this. Even though it looks complicated, I know from past experience that my moment of inertia is going to be something mr squared, right? So it's a ring, a disk, a hollow ball, a solid sphere, solid sphere. All right, it's one of those. They're all going to cancel out the R squareds there, and because all the terms have an M, the M's going to cancel out too. So I'm not too concerned. In fact, one thing you may think about doing here to make this look even nicer, or worse, depending on your standpoint, so you can factor out the m's from all the terms and get 2gh on top and 1 plus I over mr squared on the bottom. Do you see what I've done? Because we know the mr squareds will cancel out when we put in the value for I. So what do we get? We get whatever the fraction is, right? If it was a ring, it's going to be 1. If it's a disk, it's 1/2. You see what I'm saying? So we'll do the disk. So I put in 1/2 mr squared there, and that whole term becomes 1/2. 1/2 plus 1 is 3/2. Multiply top and bottom by 2/3, and we get exactly what Harishi and many of you got, 4/3 GH. This is for a disk. I could just have easily gone back and done it for a solid sphere, right? Since it's already there, I can just, it's pretty straightforward. 7/5, switch it and get V equals the square root of 10/7 GH, solid sphere. Not terrible? Let's see. Can you tell me the percentage of kinetic energy? What percent of the total energy is kinetic energy?
Good afternoon.
I'm not going to be here tomorrow for class, and I do want to speak about that, but if you're asked to find the percentage of energy that is kinetic, it's part to whole. So 1/2 mv squared is the kinetic energy, but the whole energy was mgh. If I replace that v with my square root of 4/3 GH squared, this is going to give me a term with mgh on the top. Do you see that? In fact, when I square that and multiply by 1/2, this whole thing becomes 2/3. It's not uncommon to be asked how much of the energy is kinetic. Well, 67% is kinetic, translational kinetic. That means 33% is rotational kinetic.